So this is Calc 2, and this is the derivative review. You should have downloaded the sheet of 60 problems. That's 3 days worth of work. 1 through 20 the first day, 21 through 40 the second day, 41 through 60 the third day. Let me give you some examples of how those problems can be worked, and also what I mean, I guess, by that 4 steps, showing 4 steps. You should really have no problems with many of these because you're trying to, I guess, show all your work anyway to remind yourself. So the first one, number 24. No, number 9, not number 9, not number 24. Okay. Most of these say 1 through 20, find dy dx, or find the second derivative, d squared y dx squared. If, and then we're going to give you the problem, y equals 1 plus cotangent of 2 over x, and all of that to the negative 2 power. Now, as you're doing this, don't just do it to run through the problem. Try to think a little bit, remind yourselves. If I'm trying to find dy dx, what do I see when I look at this? Well, I see u to the negative 2. That uses the power rule. And the chain rule, because I got to do the stuff on the outside first, and think of this whole thing as just one chunk of stuff in terms of x to the negative 2. And so that power rule says bring down the power, negative 2. And the u, that's 1 plus cotangent 2 over x. And for the power, you subtract 1, so it's a negative 3. But the chain rule says now you multiply by the derivative of what's inside. So I want the derivative of, with respect to x, of, this is a d, 1 plus cotangent 2 over x. Well, now I got to figure this out. So you write down, okay, dy dx. It's the negative 2 and the 1 plus cotangent 2 over x to the negative 3 times. Now, this is the sum of 2 functions, 1 plus cotangent. So you take the derivative of the sum. It's the sum of the derivatives, right? Let's put a parentheses here. So the derivative of a constant is 0. Plus, the derivative of the cotangent is a negative cosecant squared of, well, it's not just x, so now we got another chain rule coming up, and we'll leave that till later. So let's see, do I have enough? We need another set of parentheses here. Times, well, we got another inside piece to work with, the derivative with respect to x of 2 over x. So now I got to fit all this stuff together. dy dx. So negative 2, 1 plus cotangent, that's cotangent, excuse me, 2 over x to the negative 3rd power times, well, don't times 0, we're just going to, 0 plus is just going to be this other stuff. Negative cosecant squared 2 over x times, what's the derivative of 2 over x? Well, let me go back up here. 2 over x is really the same as 2x to the negative 1. So I'm going to use the power rule again. And so this is going to be a negative 2, because the negative 1 times 2, x to the negative 2 power. And now I'm down to just an x, which is that variable of differentiation that we wanted to get down to. This is the answer for number 9. Check that with the answer key. don't know if I gave you the answer key or not. Maybe I waited for the next day to give it to you. So we need to go on to another example in the 21 through 40 range. We're going to change colors and do number 24, which says find the derivative of the inverse of, now we're going to write this a couple different ways, I guess. It's going to be the function f of x, which is the same as y, which we're going to look at as ln x. And for this, we want to do it at a certain point when y equals 0. And you're going to say, well, what about x? What do we want to put in for x? Well, that's the whole point, I guess, of this thing. So, for the next 20, 21 through 40, find the derivative of the inverse of f of x, which is the same as y equals ln x at y equals 0. Why at y equals 0? Well, remember, to find the inverse, first of all, you switch x and y. So that means that this would be x equals 0 when we get into the inverse. So x equals ln y, and then you solve for y. Well, that's easier if you write ln as log base e of y, because then e to the x, this is log form, you write it in an exponential form, e to the x equals y, which is our inverse, f inverse of x. Now this x uses this 0. The y is for the function f. So let's see here. So if we want the f inverse of 0, that is e to the 0, which is 1. Now, what is, see, f of x, remember, is ln x. What is f prime of x? The derivative ln x is one of those easier ones, just 1 over x. Why do we need that? Because there is a rule. If you don't want to go through all this, because right now the derivative of the inverse at y equals 0, which is really x equals 0 for that inverse, is 1. That would be our answer. It's not a bad way to do it. But there's a rule that says also, when this might be helpful, I'm not sure, the derivative with respect to x of the inverse of x. Because the slope of a function is the derivative is a slope at a point, the slope of the inverse is the reciprocal, 1 over. So that's how you can find this derivative if you know the function f and not its inverse. It is 1 over f prime. So now you can use the function itself, not the inverse, to find the derivative. But you have to evaluate it at the inverse spot. Does that make sense? The y. So, in our case, it's 1 over the derivative of f at, well, the inverse of 0, we said was just that 1 here. And the derivative of f is 1 over x. So this is 1 over x here, but we have to evaluate that at 1, so it's 1 over 1 over 1, or just 1 when you're all done. Now this may be a really simple example, but it shows you if you want the derivative of the inverse of a function, and you're given the function, then you can take 1 over, because we're talking about slopes, the derivative. But you must evaluate it at that inverse's value at x. If that makes sense. Anyway, all this certainly is 4 steps. And this is the answer to problem 24. Should be correct in the answer key also. Another type of problem in that 21 through 40 is these directions. It says use L'Hopital's rule to find the limit of this thing. You may or may not have been taught L'Hopital's rule back in Calc I. So we might have to bring that up so you could use it. You can also use other techniques to find this limit. So let's do both ways. L'Hopital's rule says that if you plug in this value, x approaches 0, if you plug in a 0 for x for both the numerator and denominator, and you get, if I plug in a 0, I get the square root of 4, which is 2, minus 2, which is 0, over, plug in a 0 for x, I get 0 over 0. If I get this called indeterminate form, you could also get infinity over infinity. Then I can use L'Hopital's rule. If that's not the case, then I can't. So what you do is you take the derivative of the numerator individually and then the denominator individually. Now I'm going to write this as 4 plus x to the 1/2 minus 2 because that's easier over 2x. So this becomes the limit as x approaches 0. The derivative is 1/2, remember you bring that up front, 4 plus x, subtract 1 from the exponent, so it's a minus 1/2, and the derivative of a constant is always 0. Over the derivative of 2x is just 2. And then you check it again. If I plug in a 0 for x, here I get 4 to the negative 1/2, so that's square root over 4, so 2's in the, I'm not going to get a 0 here. I'm not going to get a 0 in the denominator. So this is not an indeterminate form, because you could keep going. If you got another 0 over 0, take the next derivative of this numerator and the denominator individually, and then you could do it. Now that you've got to a point where one of these is not 0, not both of them, but just one has to be. So you can say, okay, plug in a 0 for x, and you get the 1/2, 4 plus 0 to the negative 1/2, and that's over 2 because there's no x in the denominator anymore. Well, this negative exponent, and in fact this 1/2 says I've got just a 1 in the numerator. I've got a 2 from the 1/2, I've got a 2 from the 2 that was there before, and I've got this 4 to the 1/2, which was moved down there because that was a negative 1/2. So it's really 1 over 2 times 2 times 2, or 1/8. Now that's one way of doing it. That's using L'Hopital's rule. And it's sort of a cool rule. If you plug in and get an indeterminate form, 0 over 0, infinity over infinity, then you take the derivative and plug it in again and see if you get another indeterminate form. If you do, take the derivative, numerator, derivative, denominator independently until you get to one of those not being a derivative, and then you can figure out the limit. Now another way of doing that is taking the numerator, that's square root of 4 plus x, because it has that square root which is messing things up, and the denominator, and multiply by the conjugate. Think of this as a binomial, and the conjugate is the square root of 4 plus x plus 2. Now if you do that to the numerator, you've got to do that to the denominator. And now you have in the numerator, this is the sum and the difference of the square roots. This is the difference of two squares. So you square the first one, 4 plus x, because it was the square root, minus, you square the second one, which is a 4, over, well, you don't even need to multiply this stuff out. Just leave it as factors. 2x, the square root of 4 plus x, plus 2. Now, when you do that, the 4's up here cancel, and you get x over the 2x, and the square root of 4 plus 2 plus 2. And then you can cancel the x's, and you get 1 over 2 times the square root of 4 plus x. This is supposed to be an x here, isn't it? Plus 2. Now you can let that x go to 0, because you got a 1 in the numerator and a 2 times, what's the square root of 4? Well, that's 2 plus 2, which is 2 times 4, which is 1/8, the same thing. So you can solve that either way and get the right answer. Okay, because there's only 2 problems, 30 and 31, that are like this, I picked a different example so that you have 2 problems to work with. This is like numbers 30 and 31. Use the differential formula to find the square root of 16.07. That's f of x plus delta x is approximately f of x plus f prime of x times delta x. So we need our function and stuff. So what is x? X is that 16.07. I'm sorry, not x, that's just the 16. Delta x is the 0.07. Our function takes the square root of those things, because this is the x and delta x. That's what this stuff is right here. Our function f is the square root of x. The derivative of x is the derivative of, really, x to the 1/2 is a little easier using the power rule. 1/2 x to the negative 1/2 power, which is 1 over 2 times the square root of x. 1/2 is the square root. The negative means it should be in the denominator. So with those things, then we can plug this stuff in here. So this is f of 16 plus 0.07. And that's f of 16 plus f prime at 16 times 0.07. Let's see, f of 16 is just the square root of 16. F prime is 1 over 2 times the square root of 16. And this is times the 0.07. So square root of 16 is 4. 0.07, we can put that in the numerator. And 2 times the square root of 16, or 4, is 8. So we just need 0.07 divided by 8. We can do that by hand. You don't always have to grab your calculator. 0.07. Put in a few more places. Here's where the decimal goes. Doesn't go in 0, doesn't go in 7. But 70 goes 8 times. That's 64. Subtract, you get 6. 60, well, that's 7 times. 56, and there's 4. 40 goes equal 5 times here. So this is really 4 plus the 0.00. Well, this should be a 5. 875. Or 4.00875. Now on your calculator, what does it give you for the square root of 16.07? Well, let's get a calculator and find out. So, square root 16.07. According to the calculator, 4.00874. Well, we're off a little bit. Calculator says 4.00874. Pretty close, though, if you wanted to do it by hand. Now, what made this nice, certainly, is that we had a nice square root here, but you could have moved more of that, in a sense, over to this delta x. It just would have made it a little harder. The problems we have, 30 and 31, are not so bad. You should be able to do those very similarly. Another example. Do you remember logarithmic differentiation? This is number 36. Sometimes taking the log, the natural log of both sides, can split up some of these things to make it easier to work with. If you take the natural log, let me fix that. I'm moving this stuff around. Okay. If you take the natural log of y, right now we just need to write it as ln y. Take the natural log of this quotient, sine x cosine x, over the square root of x cubed minus 4. Now, the nice thing about a log is it changes multiplication into addition, division into subtraction, exponentiation into multiplication. So, left side just ln y. But now the log of a quotient is the ln of the sine x times cosine x minus the natural log of, let's write it as x cubed minus 4 to the 1/2 instead of square root. So this is then a log of a product. ln y equals, that's the sum of the logs, ln sine x plus ln cosine x minus, now we can bring this 1/2 out front, natural log, that's ln, gosh, too much stuff there, x cubed minus 4. These are all ln's, it looks like lin. That's as far as we can go as far as that's concerned. We can't split up this x cubed minus 4. It won't work with logs. But now we take the derivative. The natural log of y is 1 over y dy dx. The natural log of sine x is 1 over sine x d sine dx. What's the derivative of sine? It's the cosine. Plus, derivative of natural log of cosine is 1 over cosine. The derivative of the cosine is a negative sine x. Now the derivative of, we can just multiply this 1/2 here. The derivative of the natural log of this is 1 over x cubed minus 4. And then you take the derivative of x cubed minus 4, which is 3x squared. The 4 is then 0. Don't worry about it. So, running out of room. I'm going to multiply both sides by y. So the derivative, dy dx, is what we need to find. That's what it asks, is y times. Now you can go back up here and substitute this first expression for y if you wanted to. I'm not going to right now. Run out of room. The cosine of x over the sine of x, you can rewrite that as cotangent. Plus, or minus, I guess, because it's a negative, sine x over cosine x. You can write that as tangent. And then in the numerator for this next one is the 3x squared. And in the denominator, it's 2 times that, so it's 2x cubed minus 8. Or you can write that as a product, 2 times the quantity x cubed minus 4. Doesn't really matter. You can rewrite this a little bit, but that's pretty much it. Logarithmic differentiation made it a lot simpler. A bunch of more steps, but you need steps for my questions. Okay, this is like numbers 58, 59, and 60. but of course is a different function. We need to use the definition of the derivative to find the derivative. Given f of x equals the square root of x plus 1, we also need the first derivative for that. And let's think of this as x plus 1 to the 1/2. So this is 1/2 x plus 1 to the negative 1/2, which is 1 over 2 times the square root of x plus 1. So we know the answer. We just have to use the definition. We need f of x plus h, and that is the square root of x plus h plus 1. Because what is the definition? The derivative of f with respect to x is the limit as h goes to 0 of f of x plus h minus f of x over h. So the derivative is the limit as h goes to 0 of the square root of x plus h plus 1 minus the square root of x plus 1 all over h. We're going to multiply both numerator and denominator by the conjugate of the numerator. So the limit as h goes to 0 of the square root of x plus h plus 1 minus the square root of x plus 1 times the quantity, the square root of x plus h plus 1 plus the square root of x plus 1 over, got to do that to the denominator also, the square root of x plus h plus 1 plus the square root of x plus 1. So the numerator, because this is the sum and difference, this is the difference of two squares. So this is the limit as h goes to 0. The square of x plus h plus 1, the square root of the square root is just x plus h plus 1 minus, got to be careful here, the square of the square root, put in parentheses, x plus 1, and this I'm just going to write it as h times the square root of x plus h plus 1 plus the square root of x plus 1. Gosh, you can't fit that in there very well. So the limit as h goes to 0, x minus x cancels. 1 minus 1 cancels. The only thing is the numerator is h times that quantity, square root of x plus h plus 1 plus the square root of x plus 1. H's cancel. And I think I'm going to have to, because I'm going to run out of room, let h go to 0 now. So we only have 1 left in the numerator. This h is a 0, so it's the square root of h plus 1 plus the square root of h plus 1, x plus 1, and the square root of x plus 1. So there's 2 square root of x plus 1s. And so the derivative is that. And of course, that's what we found up here when we did it with the rule. So use the definition and from that definition we can find a bunch of rules that you guys already know. So with those examples, if you need more, send me an email and I'll get some more up here. But you have, this will work for 3 days. You didn't really have to watch all of these, just the ones you needed for the day. The first 20, the second 20, and the third 20, Monday, Tuesday, Wednesday, August 17th, 18th, 19th. Okay, get to work.